Hi, this is Andrea Hendricks. Let's talk about exponential and logarithmic equations and inequalities. We're going to talk about solving another type of exponential equation. It's type 2. We're going to look at solving logarithmic equations and then inequalities involving logs and exponents, and also how to solve a formula for an indicated variable. So let's begin with solving exponential equations. I have started here with this 3 to the x equals 9, which is a review of the type 1 exponential equation. To recall, the type 1 was the case where we could convert each side to the same base. 9 is 3 squared, so we have 3x. 3 to the x equals 3 squared, therefore x is equal to 2. Well, we're going to have equations now where we cannot convert each side of the equation to the same base. So we're going to have to use something else to solve it. And the idea is to get the variable out of the exponent. And this will use one of the key properties of logs that we talked about. Do you remember the property that said the log of x to the r is equal to r times log x? So we're going to take the log of both sides, and that will allow us to bring the exponent down so we can solve the equation. So in 5 to the x is equal to 20, we would take either the natural log or common log, it doesn't really matter, of both sides. So we would have log of 5 to the x is equal to log of 20. And therefore the left side would become x times log 5 is equal to the log of 20. So now to solve for x, we would have x is equal to the log of 20 divided by the log of 5. Now please don't make this mistake of like dividing out those logs, right? Log is an operation, it's like absolute value or square root. I can't just divide it out if it happens to be in both the numerator and denominator. Also, this is not the property that says the log of a quotient is the difference of the logs, because this has two logs, not just one. So there's no way for us to simplify that problem. So log 20 over log 5 would be the exact solution to the equation. Now if you wanted an approximation, you could use your calculator and figure out what log 20 divided by log 5 is. And it turns out to be approximately 1.86. And keep in mind how you could check, right? This is saying 5 to what power is 20? Well, you know 5 to the first power is 5. 5 squared is 25. So it has to be somewhere between 1 and 2, closer to the 2, and that just makes sense. Now this third equation, e to the x is equal to 5. If you have a base e, then you want to use the natural log. So we could take the natural log of e to the x is equal to the natural log of 5. Well, natural log and e are inverses of one another, so that just gives us x is equal to the natural log of 5. So an approximated answer would be 1.61. Okay. Or the exact answer would be natural log of 5. What about number 4? 4 to the x is equal to negative 6. If we take the log of both sides, we would have log of 4 to the x is equal to the log of negative 6. Do you see a problem with that? I'll continue. Maybe you don't see it yet. But this would be log of negative 6. So we'd have x is equal to the log of negative 6 over the log of 4. Well, if you try to compute that on your calculator, what's going to happen? You should get an error message unless you happen to have your calculator in complex mode, and then it will give you the answer. But the log of negative 6 is not a real number, and that's because we talked about the domain of log is 0 to infinity. Another way to know it is initially, right, 4 to the x equals negative 6. Well, just from a graphical perspective, 4 to the x is an increasing exponential function. Negative 6 is a horizontal line. those two never cross one another, right? There's no solution. That's because the output of an exponential function cannot be negative. So this one has no solution. So you can either think of it as the output of an exponential function can't be negative, or the input of a log function can't be negative. Now here's one that's a little bit more involved. 7 to the x plus 1 is equal to 4 to the 2x minus 3. So the variable is in the exponent, so I still need to get a way to bring that down. So I do the inverse operation, which is going to be logs. So if I take the log of 7 to the x plus 1 is equal to the log of 4 to the 2x minus 3, my exponent comes down, so this is going to become x plus 1 times log 7, and that's equal to 2x minus 3 times log 4. Now, the tricky part here is I've got to get all the variables on one side, all the constants on the other. So I need to first distribute to get rid of the parentheses. So this would be x times log 7 plus 1 times log 7 is just simply log 7. Okay, now remember this is a common log. Log 7 means what power of 10 gives me 7. So think of it in your mind as some real number. 2x times log 4 is going to be 2x log 4 minus 3 log 4. Okay. Now I need to get everything with x on one side. So we can have, let's say, x log 7, and then we're going to do minus 2x times log 4, and that's equal to negative 3 log 4, and what? We can do minus log 7. Right, so things that don't have a variable in them can go on one side. The things with a variable need to be on the other side. Now, what in the world do you do here? To get the x separated out, you've got to factor it out. So we can actually write this as x times log 7 minus 2 log 4. So all I did is I'm just removing this x from both terms. And this is equal to negative 3 log 4 minus log 7. So finally, to solve for x, I can just simply say negative log 4 minus log 7 divided by log 7 is 2 log 4. So to use your calculator to approximate that, you would need to put in parentheses negative 3 log 4, close parentheses after the 4, then minus log 7, close parentheses after the 7, and then close parentheses after the numerator, divided by parentheses log 7 minus 2 log 4, close parentheses twice. So that is approximately 7.38. Okay. Now, let's look at the last exponential equation. 6 times 1.46 minus 3 plus 5 is equal to 11. So the key is we have to have the exponent isolated. So the first thing we could do is subtract 5. So that would give us 6 times 1.4 to the x minus 3 is equal to 6. Now we need to divide both sides by 6. So we would have 1.4 x minus 3 to 1. So now we have the exponent isolated. We can apply the log to both sides. I'm using common log. All of these could be natural log. So I'd have the log of 1.4 to the x minus 3 is to the log of 1. So now we would bring down our x minus 3 times log of 1.4. And we know what log 1 is, right? That's one of those basic properties. Log 1 is 0. So what I would do to solve for x, let me see if I can squeeze this in here. If you want to distribute, you can, or you could divide both sides by the log of 1.4. I would have x minus 3 is equal to 0 divided by log of 1.4, but that would just be 0. And then we can add the 3. Okay? So x would be equal to 3. So to solve an exponential equation, you do want to use logarithms to do that. So you can imagine to solve a log equation, we're going to sometimes use exponents to solve those. If I have 4 times natural log of x is equal to 12, the whole idea is that you want to isolate the log to one side and then convert to the exponential form unless you have logs on both sides. If you have logs on both sides, then you're going to set the inner expressions equal to one another. And I'll show you that. I think I have one like that. So 4 times natural log of x equals 12. What I could do is divide both sides by 4. So we'd have natural log of x is equal to 3. But the equivalent exponential form, we have to remember that natural log has a base of e. So this means e to the third power is equal to x. Now the other thing about logarithmic equations you have to be mindful of, they have restrictions on the domain, so you have to make sure that you don't get a negative inside a log. So you can't have a negative number inside the log. Now, number 2, log of x plus 2 equals 2. It's already isolated. So remember, log has a base of 10, so this means 10 to the second power is equal to x plus 2, or 100 is equal to x plus 2. So x would have to be 98. Log base 4 of 2x minus 4 equals 3. Very similar. I'd have 4 to the third power is equal to 2x minus 4. But 4 to the third power is what? Yeah, 64 equals 2x minus 4. So we can add 4 to get 68 equals 2x and divide by 2 to get 34. So make sure 34 doesn't make the inner expression of the negative, and it doesn't, so that's okay to have. Now, number 4 involves more than one log. So when you have logs in combination, what you would need to do is use those properties that we talked about earlier that will allow you to rewrite it in terms of a single log. So if you have log base 8 plus log base 8 of x minus 2 equals 1, understand that we can rewrite that to be log base 8 of x times x minus 2 equal to 1. Right, the sum of logs is equivalent to log of the product. And now we can convert this to the exponential form. So this would mean 8 to the first power is x times x minus 2. So this is 8 is equal to x squared. So we need to solve this quadratic equation by getting it equal to 0. So we would have 0 equals x squared minus 2x minus 8. And then this one factors. So it factors as what? X minus 4 times x plus 2 is equal to 0. So they're equal to, or x is equal to negative 2. So here we have to check to make sure we don't have a negative number inside our log. The 4 is fine, right? It makes each of the log expressions positive on the inside. But if we plug in negative 2 for x, we would be taking the log of a negative number. So we have to throw out the negative 2 from our answer set and only include the value. If I have natural log of, you know what, let me make this one a little bit different just so you can see what I wanted to show you. If you have more, or if you have a log on each side, let's say this is equal to the natural log of x plus 3. If you have a natural log on each side, then what you would want to do is set the inner expressions equal. If natural log of something equals natural log of something, then that means that 4 plus 2x has to equal x plus 3. So if we subtract x to get x, it's equal to, and if we subtract 4, we get negative 1. Now we have to check to make sure the negative 1 doesn't make the expression negative. If we plug in negative 1, we get 4 minus 2, which is 2, and negative 1 plus 3 is 2, so that's okay to have as a solution set. Now I think the other form that I had was something of this natural log of 4 plus 2x minus natural log of x plus 3 is equal to 0. Well, if you have the difference of logs, just remember that's the same thing as a log of their quotient. So what I would do now is convert that to the exponential form. The log base e of 4 plus 2x over x plus 3 equals 0 means e to the 0 is equal to 4 plus 2x over x plus 3. Well, e to the 0 is 1. So 1 is equal to 4 plus 2x over x plus 3. And then you could cross multiply. Okay, so you get x plus 3 equals 4 plus 2x, which is exactly the equation that we have above, so x is negative 1. So actually, you could do this equation here in one of two ways. You could put a log on each side, or you could use the property of logs to rewrite it. Either way. Now the last one, log base 2 of x equals 1. If you have logs kind of inside each other, you've got to get rid of the outside log first and work from the outside in. So we would convert this to 2 to the first power is equal to what's inside that log, which is log base 2 of x. So we get 2 is equal to the log base 2 of x. And now we can convert again. This would mean 2 squared is equal to x. So x would be 4. So to solve exponential equations, use logs. To solve log equations, use exponents. Now, if we wanted to solve an inequality relating to the logs and exponents, we would have to do it the same way we've been doing it throughout the semester. You would find the solutions to the associated equation and then either use a graph or test points to determine which region makes it true. So if I had 3 to the x minus 6 is greater than 0, I first have to solve 3 to the x minus 6 equals 0. So that gives us 3 to the x is equal to 6. We can take the log of both sides. So log of 3 to the x is equal to the log of 6. And we would get what? X log 3 is equal to log 6. So x is equal to log 6 over log 3. You can also think of it like this, right? 3 to the x minus 6 is that exponential function of 3 to the x shifted down 6 units. And I'm running off the screen here. So envision this bottom line as being negative 6. So that's going to look something like this, right? So 3 to the x minus 6 is greater than 0. What does this x equal log 6 over log 3 represent on the graph? Right, since we set it equal to 0, that represents our x-intercept. So we know at this point is log 6 over log 3. Now you could use your calculator to find that out. But which region then would contain solutions to this inequality? In other words, is it to the right or to the left of this log 6 over log 3? To be greater than 0 means it has to be above the x-axis, right? And it's above the x-axis here. So that would be to the right of log 6 over log 3. So the solution to this problem would be log 6 or log 3 to infinity. Now if that happened to have said greater than or equal to 0, then I would have a bracket there. Now what about 2 log of x plus 2 is less than 0? So that would mean to find where 2 log of x plus 2 is equal to 0. And we could divide both sides by 2 to get log of x plus 2 is equal to 0. So remember our base is understood to be 10. So we know 10 to the 0 is equal to x plus 2. And 10 to the 0 is 1 equals x plus 2. So therefore x is equal to negative 1. Well, let's think about what this means. 2 times log of x plus 2 is just going to be a vertical stretch of the log of x and shifting left 2 units. Right. So we're still going to go through the point. What was 310 is going to be shifted left 2 units. So it's going to look like this. Right. So it says, where are we less than 0? Well, less than 0 is here, right? Have to be careful though. Our x-intercept was at negative 1, but notice our domain of the log function is only from negative 2 to infinity. So to solve this problem where it's less than 0 is only between the negative 2 and the negative 1. Our solution would be from negative 2 to negative 1 with the parentheses. If that had said less than or equal to 0, I could include the negative 1, but I could not include the negative 2. And the last objective, I know I need to hustle through this, is to solve this equation for an indicated variable. So all you're going to do is use the appropriate either logarithm or exponentials to solve for that variable. P is equal to a plus k over natural log of x. So the first thing you need to do is get rid of these fractions. And you can do that by saying that natural log of x, you can multiply every term by natural log of x. So natural log of x times p is equal to the natural log of x times a plus natural log of x times k over natural log of x. So our resulting equation, we know the natural log of x would divide out there. So we would have natural log of x times p is equal to the natural log of x times a plus k. So we want to get the terms for the natural log of x on one side. So we can subtract the natural log of x times a. And now we can factor out the natural log of x to have this as natural log of x times p minus a is equal to k. And then we can divide both sides by p minus a to get natural log of x is equal to k over p minus a. And then the last thing we want to do is apply the exponential form to get this out of the logarithmic form. So again, it's natural log, log base e. So we know that e to the k over p minus a is equal to x. And that is it. So if you have any questions on exponential and logarithmic equations, don't hesitate to contact me. Thanks.